Hello, students! In this explainer, we're going to do things a little differently. Instead of just trying to memorize all the facts and formulas from the electricity chapter, we're going to connect everything into one single story. The idea is to make your exam revision much, much simpler and a lot more logical. Okay, so here's our roadmap. We'll start with a story of electric flow, then look at Ohm's law and resistance, combining resistors both series and parallel, the effects of current like heat and power, and then, very importantly, we'll talk about avoiding common exam mistakes, and I'll give you a strategy guide for your exam. Let's get started. All right, let's begin our story right at the start. Before we can understand, these big complex circuits, we first need to ask a simple question. What is electricity? What makes it move? And it all begins with the idea of charge. So what exactly is electric current? Well, you can think of it as simply charge in motion. That's it. Imagine a river. The flow of water is the current. In a wire, the flow of charge is the electric current. We measure how much charge, which is Q, passes a point in a certain amount of time, T. So our formula is I equals Q by T. And the unit we use for this is the ampere, or A for short. Okay, so charges are flowing. But what makes them flow? Why do they move at all? Let's go back to our river analogy. Water only flows from a higher level to a lower level, right? There needs to be a difference in height. It's exactly the same with electricity. Charges need a sort of electric push to get them moving. We call this push the potential difference, or more commonly, voltage. It's the work done to move the charge. Without voltage, there's no push, and so no current. It's as simple as that. So now we have the push, which is voltage, and the flow, which is current. The next logical question is, how are these two related? This brings us to probably the most important relationship in this entire chapter. And it introduces the third main character in our story, resistance. Imagine you're trying to walk down a very crowded hallway. It's difficult, right? You keep bumping into people. This is exactly what happens to charges moving through a wire. They collide with the atoms of the conductor. This opposition, this electrical friction, is what we call resistance. It basically resists the flow of current. And we measure this resistance in ohms. And this is where it all comes together. A scientist named Ohm discovered a beautiful, simple relationship between our three characters, voltage, current, and resistance. It's called Ohm's law. It states that the voltage across a conductor is directly proportional to the current flowing through it. And the constant that connects them is, you guessed it, resistance. This gives us that golden formula. V equals I multiplied by R. You are going to use this formula a lot. Now, a great way to see Ohm's law in action is with a graph. If you plot voltage on the y-axis and current on the x-axis, for a conductor that follows Ohm's law, you get a perfect straight line that goes through the origin. And what's really useful is the slope of this line. The slope, which is V divided by I, gives you the resistance R. So a steeper line means a higher resistance. This is a very common question in exams, so please pay close attention to this graph. Okay, so we know what resistance is. But what determines the resistance of a particular wire? Well, a few things. First, the length of the wire. Think about it. A longer journey means more obstacles, so a longer wire has more resistance. Second, the area of cross-section, or how thick the wire is. A thicker wire is like a wider road. It's easier for the charge to flow, so it has less resistance. And third, the material itself. This is a property called resistivity, represented by the Greek letter rho. All of this is captured in one formula. R is equal to rho times L divided by A. So far, we've only talked about a single resistor. But in real circuits, you almost always have more than one. So how do we combine them? Well, there are two basic ways to connect resistors together. We can connect them in series, or we can connect them in parallel. And here you can see exactly what that looks like. On the left, you have a series circuit. See how the resistors are connected end to end? This means the current has only one single path to follow. But on the right, you have a parallel circuit. Here, the resistors are connected across the same 2 points, which means the current comes to a junction and has to split up, taking multiple paths. This table is incredibly important. Let's break it down. In series, since there's only one path, the current is the same everywhere, but the voltage gets divided among the resistors, and the total resistance simply adds up. It increases. Now, in parallel, it's the opposite. The voltage is the same across each resistor, but the current divides. And here's the interesting part. The total resistance actually decreases. The formula is 1 upon Rp equals 1 upon R1 plus 1 upon R2, and so on. Now, a very important exam tip. Please remember,
After you calculate 1 by RP, you must take the reciprocal to find the final answer for RP. So many students lose marks on this.
So let's think about a real-world example. Your own home. Have you ever stopped to wonder why your house is wired the way it is? I mean, if one bulb fuses, the TV and the fan and everything else still keeps working. Why is that? The answer is all about series versus parallel. And the answer is, our homes are wired in parallel. This is a very, very common exam question, so listen carefully. There are a few big advantages. First, every single appliance gets the same full voltage. In India, that's about 220 volts. Second, you can turn each appliance on and off independently with its own switch. And third, just like we said, if one appliance stops working, it doesn't break the circuit for all the others. They keep running. Okay, so we've seen how current flows through circuits, but the story doesn't end there. When current flows, it has effects. The electrical energy gets converted into other forms of energy. The most common effect, and the one we'll focus on, is the heating effect of electric current. This leads us to the next part of our story: heat and power. This heating is described by something called Joule's law of heating. It tells us that the heat produced in a resistor is directly proportional to three things: the square of the current, the resistance, and the time for which the current flows. The formula is H equals I squared RT. And you see this everywhere. It's the reason an electric heater works, why a toaster makes toast, and even why your laptop gets warm after you've been using it for a while. Now, this heating effect can be incredibly useful, but it can also be dangerous. So we have a very clever safety device that actually uses this effect to protect us. It's called an electric fuse. A fuse is just a small piece of wire with a very low melting point. If the current suddenly becomes too high, the fuse wire heats up very quickly, melts, and breaks the circuit. It sacrifices itself to save our much more expensive appliances. Next up is electric power. In simple terms, power is just the rate at which energy is used. So a 100-watt bulb consumes energy faster than a 10-watt bulb, which is why it's brighter. We measure power in watts. Now, you'll see a few different formulas for power. P equals V into I, P equals I squared R, and P equals V squared by R. They are all derived from each other. The one you choose to use in a numerical problem just depends on what information you've been given. Finally, let's connect this to your electricity bill at home. When you get that bill, you're not being charged for power. You're being charged for energy. Remember, energy is power multiplied by time. And the commercial unit of energy, the unit on your bill, is the kilowatt hour. This is simply the energy used by a 1,000-watt appliance running for 1 hour. And for your general knowledge, 1 kilowatt hour is equal to 3.6 times 10 to the power of 6 joules. Okay, that brings us to the end of the story of electricity. We've covered all the main concepts. But knowing the concepts is one thing. Not losing marks because of silly mistakes is another. So let's spend a few minutes on the most common errors students make in their exams. First, and this is a big one, unit conversion. Always, always check your units. Time must be in seconds, length must be in meters, don't get caught out. Second, placing the meters. Remember, ammeter is always in series, voltmeter is always in parallel. Third, choosing the right formula. Look at what's given in the question and pick the power formula that fits. And fourth, I'm saying it again because it's so important, with parallel resistance, after you find 1 by RP, don't forget to find the reciprocal to get RP. All right, last section. You know the concepts. You know the mistakes to avoid. Now, how do you present your answers to score maximum marks? Your presentation really does matter to the examiner, so let's quickly go over a few tips. Okay, listen carefully. For numericals, follow a system. Always write given, then write the formula you're going to use, then show the substitutions, and finally, write your answer with the correct units. This structure can get you partial marks even if you make a calculation error. For diagrams, please use a pencil and a ruler. Make them neat and label everything clearly. For your theory answers, underline the main keywords. It helps the examiner see that you know what you're talking about. And of course, keep your work neat. And that's it. That is the complete story of electricity. We've gone from the very basic idea of charge all the way to how your electricity bill is calculated. You can see now how every single concept connects to the next one. You have revised the entire chapter, you are well prepared, so go into your exams with confidence. All the very best.